Verzeo, your one stop solution to everything learning.
Okay, so for today's session, the pre-requirement is knowing recursion. All right, so is there anyone in the session who doesn't know recursion? If yes, then probably you won't understand a few things, but you can still continue watching. But very less chances that you'll understand a lot of things if you don't know recursion. So I'll say the recursion is the pre-requirement for today's session, and the agenda looks like this. Well, I'll give you a little hint about like the session today is about backtracking. And I'll give you a hint about what backtracking is initially to begin with. Then we will do two questions without knowing exactly what backtracking is, but we are all programmers and we will get a problem statement and we'll try to solve it with building our logic by ourselves without knowing what backtracking is exactly. And then we will solve basically two questions using the same approach. Basically, we don't know backtracking, but we are still trying to solve two questions, and we will notice something in the two questions that will lead us to understand what is backtracking. All right, and I want to do it that way because that way I think you will get it more clearly that what exactly is backtracking and why is it even needed. Then we'll define backtracking, and then I'll share a backtracking weapon kind of thing, like using which you will be able to solve most of the backtracking problems, kind of a template that you can apply to solve any backtracking problem. And then identification of problems. How do you identify this particular problem can be solved with backtracking? And then we'll solve one more question, dice roll, if time allows. If not, then I'll leave this question for the assignment. But if time permits, I'll solve that. Okay. So this is the little hint that I've been talking about. You see a maze in this on the screen right now. This is the starting point and this is the finish point. You start from one point and you have to reach the finish point. Basically, you travel like this, with this, with this, with this, with this. Ultimately, you reach some point, right? All right. Basically, let's say you are on this particular position here. At this point, you have two choices. Either you can go to the right or you can go to the left. But while you go to right, you are blind. Okay, let's assume that you're blind and you do not know whether it's the right path or not. So you go to the right, but then you realize that there is a wall here and this is not the right path. So you come back. Basically, you backtrack and you come back to the original position, right? That is what you're doing. Then you go to the left path. By going to the left, you come here, and then at this junction, again you have two choices: go upwards or go downwards. Let's say you go upwards because you cannot see what lies in the future. So you make the choice whatever is available, and you go upwards, and you keep going upwards, and then you realize that there is a block, and this path is also not correct. So basically, you have to come back. You are undoing what you did. You are backtracking to original place, and then you come back here and make the downwards choice. Make the downward choice and come at this junction. At this point, again, you have two choices: either go to the right or go to left. If you go to left, you again get blocked and you have to backtrack again to the original position. And if you make the right choice on the right side of it, you actually reach the finish point. This is kind of a hint for what backtracking is. What we have done, like what we have seen in this particular example, is you have some choices, right? And you make those choices. Like you had the choice of going either to right or to left, or you had the choice of going upwards or downwards. So there was a space of possibilities. Basically, if I give it another name, we had a space of possibilities, and we choose one of the possibilities. Basically, we choose all. We have, because we don't know what's gonna happen, so we choose all of them and then see what leads us to the correct path. Maybe this was leading us to the correct answer, and this was leading us to the wrong answer. Let's say we went for the left choice first and we reached on the wrong answer. So we go back, we backtrack, or we undo things. What we were doing in one choice, we were making that choice. And if after we made that choice, doesn't matter because we have to explore all the paths, right? So we make that choice and then we undo that choice and come to original state. Basically, you went to left, you were standing on a junction and you went to left. But before going to right, you have to come back to the junction also, right? So that is what is signified by the term original state. That is kind of a hint. All right. Now we will solve a couple of questions and then we'll see like the exact definition of backtracking. The first question is you have to write a recursive function, print all binary, that accepts an integer number of digits and prints all binary numbers that have exactly that many digits in ascending order, one per line. Just a second. So if let's say this is what we had, this is not the answer. This is the answer. Let me explain the question first. So let's say if n is given 2, then you have, what is a binary number? I hope you all know. If not, then a binary number is a number having only zeros and ones in it, right? So if I want to have all the binary numbers of length 2, what are the possible binary numbers? It could be 0, 0, 0, 1, 1, 0, or 1, 1, right? Only 0 or 1 basically inside the choices that we have. And print all binary number 3. If n is given 3, then these are the possible binary numbers that could be made, right? Now let's try to think of a solution of it. We do not know what is backtracking, right? No relation to backtracking. Let's just try to solve it without actually thinking about it. We will just use the knowledge that we have, assuming that you are in the backtracking session, you at least know the concepts of recursion. So by using that knowledge, we'll try to solve. Okay. So let's say n is given 3. So basically we have 3 places, right? In each of the answers, there were 8 answers. For n equal to 3, there were 8 answers, right? For each place, either it had a 0 or it had a 1, right? So for each place, there were 2 options. For 0th index, there were 2 options. Either 0th index had a 0 or 1 on it. Second index had a 0 or 1 on it. And similarly, the third index also had either a 0 or a 1, right? That's how we form 8 answers. 2 choices on it, 2 choices on it, and 2 choices on it. And how did the answers look like? 0, 0, 0, 1, 0, 1, 0, something like that, right? So if we try to make a decision tree or a recursive tree kind of thing, then we have 3 indexes and we have n equal to 3. Let's say we are working on the 0th index, right? For 0th index, what choices do I have? This first place could either be a 0 or it could be a 1, right? So n was 3, but on first place I have written 0. On first place I have written 1. But how many places now are left to fill? Now only 2 places are left. So n would become 2. At this point, I again have 2 choices for the first index. This is the first index. I'm talking in terms of 0-based index. This is 0 and this is 1. This is 0 and this is 1. 0 is on the first index already. So it had 0 already and n would become 1. N would, let me write the value of n with a different pen. N would become 1 for all of them because we have made the second, like we are filling the second index. So 0 was already there. If you see, I'll write what was already there with a green pen. So 0 was already there and 0 was already there. In this case, 1 was already there and 1 was already there. And now we are making the choices. Let's write the new choices with black pen. So on the second index, now we are actually filling the second index in this particular column. The second choice we are making is of having a 0 on the first index. On this index, it's a 1. On this index, it's a 0. And on this index, it's a 1. We still have 1 place left, right? Because the n was initially 3. And this n equal to 1 also represents there is 1 number still left that we have to fill. Still 1 place still left. So for this particular place, the second index, now again there are 2 choices. Either it could have a 0 on it or 1 on it. So either 0 or 1. 0 or 1. 0 or 1. What we already had, let's write that with a green pen first. 0 and 0 were already there. 0 and 0 were already there. 0, 1 and 0, 1 were already there. 1, 0, 1, 0, 1, 1 and 1, 1. What is this? This is actually what was already there in the answer. So this, before making the choice, we already had 1, 1 in our current answer basically. So that is what the green color are representing. The green colors are representing. The current choice that we have to make. Also, another point to notice is like n would become 0 now. For all of them, n would become 0 now. I'm not writing it on all the places, but I hope you get it. For the final choice, this third index could have a 0 on it or it could have a 1 on it. Like see the branches that are. It could have a 0 on it or it could have a 1 on it, a 0, and a 1. So let's count how many answers do we have. 1, 2, 3, 4, 5, 6, 7, and 8. We have 8 answers in the leaf node, and aren't they the answers that we want? These are the answers that we wanted. So one thing is clear, that we are getting our answers when n becomes 0 on all the leaf nodes. Leaf nodes contain our answer. And when do we reach the leaf nodes? When n becomes 0, right? So basically, if I talk programmatically, then I have to do I have to do both the things basically, but one at a time, right? Any problem in the tree that I've drawn, if I do not get any no's in the chat, I'll assume that the tree is clear. But if you tell me that you have any doubts or concerns, you can unmute yourself or you can type in the chat. All right. Then I'm assuming that the tree is clear. So basically, how would the function that would be given in the program would look like? It would look like something like this, right? Print all binary would be given, and only print all binary would be given. But we have a vector, a current array taken. We could take it as a string also. I've taken it as a vector for now. What is a vector? For Java and other language people, I'm writing the code in C++, but vector corresponds to any linear data structure in your particular language. For Java, it could be an array list. For Python people, it could be a list. It's nothing, basically, it's just an array, right? And why I need an array? Why do I even need this? So see, these answers, all these things needed to be stored somewhere, right? This 0, this 1, this 0, 0, this 0, 1, this 1, 0, this 1, 1. These answers, these have to be stored in a data structure, right? These have to be stored somewhere. And where are they stored? They are stored in a vector called as current. It's an array. And because we were using the indexes, so like you understand, current would be an array of length 3. Basically n, if n is 3, right? And we are trying to fill each index one by one. Current initially is empty. Current initially doesn't have anything, right? Because if you start with the tree at the first place on the root node, then this particular array is empty, doesn't have it. When n was 3, we did not make any choice at all, and all of the work is yet to be done. Basically, that's why initially the array is an empty array, empty vector. Okay. So what I had, like, I had two choices at every point, right? What were the two choices? Either current would have, what was the choice one? Like either we would append 0 in the current answer, or the choice 2 was append 1 in current answer, right? Makes sense. That's what we wanted from the tree. I'm again saying, if there are any doubts, feel free to unmute yourself or ask on the chat. I can explain again if something is not clear. So how do you make that choice actually? You append in the current answer, you push back 1. Pushback is nothing but just an operation of inserting something in there. Once you made the first choice of pushing back 0, actually it's 0, it's not 1. Now this is where recursion comes into play, and that's why it was a pre-requirement for these sessions. So you made one choice of appending 0 at this particular point, but after this, you will ask recursion to do the rest of the work for you. You will ask recursion to do it for you, and you would just make one choice at this particular point by yourself and ask recursion to do the rest of the work for you. So we'll make a recursive call with this current and all binary. What would be the value of n that would be passed? N would be decreased by 1, isn't it? If you remember from the diagram that we were making, for first call n was 3, and in each call we were decreasing n, because that is how we will recognize how many places are still left to be filled. And current we have already modified, so current would be this. And the second choice was of appending 1, and again making the same recursive call. Now there is one thing that we have not done yet in all the recursive codes. You need a base case. And what was our base case from the tree? When n becomes 0, then we print the current answer. I've written a function called as print. This just prints the vector that has been passed to it. All right. So instead of writing the same thing here, I have made it as a different function. Basically, this would just print it. Now, excuse me. Yeah. So with this code, should it work? Any answers in the chat? Should this code work? From the tree that we saw, we had two choices to make. Either we would put 0 in the current answer, or we would put 1 in the current answer and ask recursion to do the remaining work. That's all right. So it should work, right? It would be great to see some answers in the chat. I think it's for the first time that the audience is not at all interactive. Okay, let's try to run it and see if we get the correct answer or not. Let's put 3 itself in the input. So we received this as the output, but this was not supposed to be our output, right? This is wrong. And why this happened was, let's see that. Why we got wrong answers here. So remember from the diagram, we had to undo our choices. If you remember, we were standing at this particular point and we went here on one path and we had two choices here, either to go down or to go upwards, right? So to make let's say you went down, right? And you realized that, okay, this is not the right thing to do. I have to go upwards. But to go upwards, you have to reach the original point, right? You'll come back. So basically in the code, what is missing is we have not done the coming back to original state wala step. Original state has not been achieved after making one choice. So we made the choice, but we made the choice, but we did not undo the choice to reach the original state. This is the problem in the current code. You will understand it when I will do a dry run more clearly, but on a high level, this is what is happening. So this code could be corrected just by undoing that choice. Basically, if I try to explain it once again from the tree. So you see, at this particular point, I made a choice of pushing 0 in the current answer, right? So whatever recursion did, I don't care about that. But at this point, my current is 0 and I want to make the choice of appending 1 in the answer. But to make that choice, I have to remove this 0, right? If I don't remove this 0, what will my current answer become? 0 would be already inside it, right? 0 would be already inside it after this particular call has completed. And I will make another call of pushing 1. So I will push 1 after 0. So current would become this for this call. But what I wanted for this call, current should have been only 1 and not 0, 1, right? That is why it is important that before you push 1, you remove 0. So basically, before you make the next choice, you have to undo the previous choice. Basically, you have to pull out the 0. You pushed 0 inside, but before appending 1 in it, you have to push out that 0. Pop out that 0. So current dot pop back would pop that out. Okay, now it should work. Yes, see, that is what the answer was. Is it clear, guys? Is the question clear? I'll do a quick dry run of how the code has worked, right? We'll just do a quick dry run of how it's working. Do we need a dry run? Let's actually do the dry run for at least one question. So if it is clear, then we can actually skip the dry run. If anyone wants, I can do the dry run. Could you explain? Then yeah, let's do that. Let's do the dry run. That to some people it's clear and to some it's not. So with dry run, you will understand that how it's actually working. Okay. Let's take a smaller example. Let's take n equal to 3 only. This is, let me copy paste the code. So n is 3 and I am on this line. N is 3 and is n 0? We'll check. Is n 0? No, n is not 0. So let's remove this a little bit. And I'm calling the function as f only. So initially n is 3 and the vector is empty. This is current. All right, this represents current and this represents n. I check n is 0. No, n is not 0. So I come on this line. Current dot pushback 0. Let's maintain current here. This is current. If you see current is being passed as a reference, if you don't pass it as a reference, you will be repeatedly making you will be using a lot of memory in the recursive calls again and again. So notice that it has been passed by reference. So it won't be changed in different recursive calls until and unless you change it. So current initially is 0. Basically it's nothing. And on line number, let me name these lines. Let's call them 1, 2, 3, 4, 5, and 6. Okay. So I come on line number 1 and I push back 0 in current. So current looks like this now. Now I call print all binary with I inserted 0 inside current and subtracted 1 from this, and current looks like this. So basically how our stacks look like in the stack call stack, first function is this, and on top of it we have this function. Will we go on line number 3 from here? This is on line number 2. Okay, this is line number 2. We can't go on line number 3 until and unless this function call has been completed. So we'll again go on top of the function and we'll check if n is 0, n is not 0. So we'll again come on line number 1 and we'll again push back 0 in current. So see, current is 0 right now, and we are again pushing back 0 in it. And on line number 2, we again come on line number 2, but where we have come on line number 2 this time from this function call, and not the top one. For this function call, we have reached line number 2, and we are making another function call by decreasing n and with the current answer. And what is the current answer currently? Look at this part for current answer. This is all separate. Current looks like 0 0 only, right? So this is this, and after line number 2, you again go on top of it because this is a function call. You can't come on line number 3. You check n is 0, n is not 0. You again push back 0 inside current. So you push back 0 inside current. So function call on line number 2, again another function call is happening. N 0 and becomes 0, and all of these become 0 0 0. Now you again go on top of the function call and you check for the base case, is n 0? Yes, n is 0 right now. So what do? You print current, right? So basically, let's write our answer also somewhere. Whatever we are printing, I will write it on the top of the screen. Okay, so we are printing 0 0 0. This is what we are printing. This is what we are printing. Our prints 0 0 0 we have printed already. Or from this line we are printing it. From this function call we are printing it. And after that we have returned. Basically, if a function returns, what it means that it would be erased from it would be removed from the call stack, and the execution control would return back at the place from where the function was called. And where the function was called, it was called at this point, right? It was called on line number 2 inside this function, right? So this line number 2 has completed. Now line 2 completed for this function, right? This function completed, and for this function line number 2 completed. After line number 2, we will go on line number 3, which says pop back current. And what current looks like right now? Current is 0 0 0, and this now they are asking us to pop back. Pop back means whatever is on the last index, remove that. So we will remove the last 0. This 0 has been removed. Okay. Now I will come on line number 4. What's happening on line number 4? On line number 4, I'm appending 1 in the current answer. So what is the current answer right now? Current answer is 0 0. But from line number 4, I add 1 to the current answer, right? So current answer would look like 0 0 1 now. Current answer would become, I am writing it here, 0 0 and 1. 0 0 and 1. Now I go on line number 5. I have made the next choice of choosing 1, and I have reached line number 5, and I am making another function call with n minus 1. N was 1 here, so n minus 1 would become 0, and this would become current is, what is current? Current is 0 0 1. So you go back to the function and you check if n is 0. So n is 0, yes. So you will print current, right? If you print current, what is current right now? Current is 0 0 1. So you printed once you have already printed this 0 0 and now you are printing 0 0 1. 0 0 1 is also printed. And after printing, you are on this line for printing and you return. What would happen if you return? This function call would be removed from the call stack, and you would come back again on line number. Where was this call returned? This call was returned at this point, line number 5, right? Basically for the function f100, you completed line number 5, and this function call would return the execution at this particular point. So this would be completed, and we can now execute the line number 6. And what's happening on line number 6? We are doing a pop back, right? So what would be removed if we do a pop back? The last one would be removed, and this one would be removed. Then yeah, is it clear until now? Is the dry run clear until now? Until this point of time? Because I want to make sure to not, I'll have to repeat everything if it's not clear. Okay. So you will pop back 1 from it, and then you would have reached the end of the function. And when you reach the end of the function, it means the function has completed, and now it would be removed from the call stack. So this function would be removed from the call stack now. So we have completed 3 function calls. This function call has been completed, this function call has been completed, and we have also completed the line, this particular removed the this call as well on line number 2. Now when this function call would return, where would we go? From where this was called from, right? So this was called from function 20 at line number 2. So this was actually this, right? So we have come back on line number 2, and now we are free to execute line number 3. What's happening on line number 3? We are popping back another thing from current, right? And I hope this popping backs now makes sense, because if, let's see, if you would not have, at this point, if you would not have popped back this particular 0, you would have given 000 and 1 to this call, right? Which was wrong. So that's why popping this 0 was important, right? If you see the internals of it now. So we make another choice of, like, we are on line number 4 now, and we push back, and let's remove that 0 also. This was the 0 that we, on line number 3 we are popping back, so this 0 is also popped back, and we will add 1 to the current. Now current would become 1 because on line number 4, this is line number 4. On line number 4 we are adding 1 to current, right? After line number 4 we go on line number 5. This is actually line number 5. On 4th we added 1 to the current answer. You check is n 0, n is not 0, so you come on line number 1 and you push back 0 in current. So current would become this now. So if you push back 0 inside it, I'll erase the tree from bottom to draw the other parts of it. Why is this eraser not working? Okay, I will use a different pen for these calls. So I'm making them here because of space constraints. So if I make the call of 0 and if I make the call of 1, so this would look like F1, and current would become 0, 1, 0. And this particular call of this function 1, just a second, I'm trying to use this eraser, but it's not working. Anyway, so basically I have drawn one part of the tree like that, and for the rest of the tree similar things would happen. And I'm not sure why this eraser has stopped working suddenly for me, but I hope you get the gist of the dry run here. So the whole point of explaining this was why this current dot pop back line is important, and I hope now you have understood that. At this point, like, let's say if I go back to, let's assume that this call has been completed, because we are also running out of time a lot. So at this point, current would be 0, right? And you, for making the next call, current should be empty. Before pushing 1, we should remove the 0, right? So this 0 would be removed by calling current dot pop back. And from here, like, similarly, all this tree, like, similar things would happen for 1. I hope, like, I know we have not done the complete dry run, but I hope you get the gist of what's being done here. If that is clear, like, is it clear, Tanya, now? If that is okay, we can move to the next question, or probably to the definition. We have 20 minutes, right? We can do one question. Okay. All right. Let's see the other question then. The other question is generate parentheses. And the question is that you are given a number 3, and you have to generate all valid parentheses of having 3 opening brackets and 3 closing brackets. So n represents the pairs of parentheses. So if n is 3, you have 3 opening brackets and 3 closing brackets, and you have to generate all the possible combinations, valid combinations, with 3 opening brackets and 3 closing brackets. Right. So let's say if n is 2, then what could be the possible correct combinations? One is this, another correct combination is this. These are correct combinations. There are more combinations of it. Like, you could write something like this. This is also having 4 brackets, but this is not valid, right? This is not a valid parenthesis. So I hope we all understand what is valid parenthesis and what is invalid parenthesis. Okay, so this is the question. I hope, is the question clear? Okay, so let's say n is given 3 to you. Let's take the example. Is second one valid? Yes, second one is also okay. 2 opening brackets and 2 closing brackets. Yes, this was an extra bracket, closing bracket. So one thing is clear, that if n is 2, the length of each of the valid parentheses would be 2 into 2. This is 2 into n, which is quite obvious because you have two opening brackets and you have two closing brackets. Sorry. So let's say n is given as 3. So you have how many open brackets? You have 3 open brackets and you have 3 closing brackets. And just like the previous question, each of the position, like we have 6 positions right now, 0, 1, 2, 3, 4, 5. Why 6? Because the length of the answer would be 6. This is the current answer. And each of the position have 2 options. Either it could have a opening bracket or it could have a closing bracket, right? But not all of the combinations would be valid. So let's say open is 3 and close is 3 and n is 3. So you have the choice of either using a open bracket or a closed bracket on the current answer. This is our current answer, and current answer is empty right now. What would n become? N would become, let's leave n, and let's go with open equal to 3 and close equal to 3. I have used one opening bracket, so I have consumed one opening bracket. So how many opening brackets are left with me? 2 opening brackets are left with me. This is open. And how many closing brackets are left with me? Three of them are left with me. So I will not write O and C on all of the parameters now. So whatever is on the right represents closing brackets available, and whatever is on the left represents opening brackets available. Okay. And what would be the answer look like? What would the answer look like right now? It would look like just a single opening bracket. This is our current answer. If I make the choice of, let's first explore this part only. I made the choice of using an opening bracket. For the next index, again, I have 2 choices, either use an open bracket or use a closing bracket. If I use an opening bracket, the number of openings brackets left with me would be only 1 and closing would be 3 because I have not used it. So current answer would look like this, 2 opening brackets, right? If you don't understand anything, please ping on the chat or unmute yourself. Okay. If you use a closing bracket, open would remain same, but closing would decrease by 1. And what the current string looked like, the previous string basically, in the current string in the previous call looked like an opening bracket, and you are appending a closing bracket to it. So it would look like this now, an opening and a closing bracket. At this point, again, you have 2 choices, using an open bracket or using a closed bracket. If you use an open bracket, then open would become 0, close would remain 3, and the string, basically the current answer would look like 3 open strings. If you use a closing bracket here, this would remain 1, this would become 2, and this would become this. All right. At this point of time, let's explore, like let's get to one answer at least, and then we'll see opening and closing. Can you use an open bracket now? You cannot use an open bracket because you have already exhausted all the opening brackets that you had. Now you do not have any opening brackets left with you at all. So this is not possible. Open has become less than equal to 0. So that's why this is not possible. You can put a closing bracket here, of course. Open would remain 0. This would become 2. And this is the new closing bracket. At this point, you will have 2 choices, open or close. Open is not possible because open has already been exhausted. So this would become 0, 1, 3 openings and 2 closings. Again, 2 choices, open and close, not possible, 0, 0, and 3 openings and 3 closings. So now are there any choices left with us now? No, we have used all the 3 brackets, 3 open brackets and 3 closing brackets. So we have reached one answer at least. And when we have reached the answer, when we have exhausted both the open and closed brackets. So one thing that is clear, that we are reaching our answer when both open and closed become 0. Okay, let's see some more decision points to understand it more. Where were we? Yeah, let's see this part of it. Change the color, okay, to make some distinction. At this point, you have 2 choices. Basically, let's talk about this choice first. Or even let's go top of it. If I go on this particular choice, or let's solve the tree from bottom itself. We were here and we had an opening bracket, like the current string looked like this right now. And we had 2 choices. We could either have an opening bracket or we could have a closing bracket at this point. This was also one thing that is not yet explored. At this point also, we could have an opening bracket or a closing bracket. So for this choice, if you choose an opening bracket, then this would become 0. This would remain 2, and opening, you are having an opening bracket. So opening this was what was already there and you put an opening bracket here. If you make the other choice, 1 would remain 1, this would become 1, and you will append a closing bracket at this point. Here also you will have two choices, either use an opening bracket or a closing bracket. Here you will have again two choices, opening and closing, but opening choice is not possible because opening brackets have already been exhausted, right? Let's see for this tree. If you choose to have an opening bracket, then this would become 0, this would remain 1, and this would become this. Okay. If you choose to have a closing bracket here, let's see. This is very important now. Listen very carefully to this. If I choose to go with this choice to have a closing bracket at this particular point, then can I do it or not? Let's see. If I choose to have a closing bracket, open would remain 1, close would become 0, and the parentheses would look like this, right? So you see there are 2 opening brackets and there are 3 closing brackets, and whatever you do after this would be done after this bracket, right? Nothing can be changed in the prefix, but this is itself invalid. We have reached an invalid state, right? This is invalid. We cannot have 2 opening brackets and 3 closing brackets. Basically we reached a wrong state, so we will not make this choice. If you have seen examples where we were discarding the option where left was becoming less than 0. If left was becoming less than 0, we were not making those calls, right? In fact, even equal to 0. If it was equal to 0, it means that it was exhausted already. For right, if right is becoming equal to left, we are not making this choice because that is an invalid choice. Are you getting this point? So basically you will make this call only if you right means close and left means please, I'm sorry if I use 2 different variable names. So we will make this call only if the closing brackets are basically the right brackets are greater than the number of the left brackets. The second choice would be made only if the closing brackets would be greater than the opening, or if it has become equal, you will not make that choice. You can see that in another, like on the top level of it also. If you try to make this choice, closing bracket, open would remain 3, close would become 2, and the current answer would look like this, which is not a valid choice. So any call that would lead close to become less than open is not a valid choice. So what are valid choices? Only when close is greater than open, those are the only valid choices that we will make. Basically, in this question also, we are having a decision tree. We are having 2 choices at every step. Either use a opening bracket or use a closing bracket. These are the 2 choices at each step. And from the last question, we have to undo the choices that we are making, right? That is the gist of the question. Let's try to write some code. We need to store the current answer, right? So we need a data structure for storing the current answer. So let's put that. We have to return a vector of strings. We'll be having our answers in result string. This is actually the result that we would return. Ultimately, we will put all the answers in this result, and current is the current string, like which would be passed with every recursive call. And we will make a helper function. We need a helper function because we need to pass more parameters than just n. What parameters do we need to pass? We need to pass the result because this is actually the answer. Okay, let me call it answer. And we need to pass the current string, and we need to pass 2 more things to it. We need to pass answer, we need to pass current, and we need to pass how many open corresponds to left and close corresponds to right. So how many left brackets do we have available, and how many right brackets do we have available? Right brackets available. Basically, initially how many left or right brackets are available? All of it is available. We have not used anything. So n and n would be passed. And after making that call, we will return the answer. Why? Because we will be passing this answer by reference. That's why once this call has been completed, we can directly return answer. Let's write helper function here. Vector of string answer string, which is either current, you can call it current or str, whatever. It's just a variable name. Int left and int right. So let's write the base case first. What was the base case? We talked about it while we were making the tree, that when we would exhaust all the open and close brackets, exhaust all open and close brackets exhausted. Basically, if both left and right become 0, if left is 0 and right is 0, that is when we have reached the base case. And what we will do in the base case, we will put the current answer in the answer, current string in the answer, and we will return. Right, that is the base case. Now we have two choices. Choice one is to append an opening bracket or a left bracket. And what we do after that, we call recursion, right? We call recursion and result answer basically. The current string left would decrease by 1, right? If you remember, if you have chosen to use an opening bracket, a left bracket, then left would decrease by 1 and right would remain same. After this choice, after the call has been completed, you have to undo the choice. And how do you undo? You undo by popping back. Like you inserted an opening bracket, but to make the next choice, it is important to remove the choice, go back to the original state basically. And the choice 2 is pushing back a closing bracket and helper answer. Current would remain current, left would remain left, right would become right minus 1 because we have used a closing bracket, and then we will pop back. That's all. That should work. It's not string. I've called it current. Something is wrong when we did not give invalid statement. Yeah, right. So there is one problem. Like we discussed one thing, that if left has become 0, we cannot reduce it more. So this call would be made only if left is greater than 0, right? Otherwise, this call should not be made. And when should this call be made? This should be made only if right is greater than left. Now this should work. Yes. So we made some choices and we explored only valid paths. For the invalid paths, we have to discard them because if we do not, we will keep doing -1, -2, and we'll never reach a valid state, and that would lead us to finite call space. Okay. So we solved 2 questions. Now let's go back to some theory and how things are working. I hope both the questions are clear. So what is backtracking? Backtracking is a problem-solving strategy which explores all solutions and picks desired solutions and discards undesired solution while maintaining original state. This line is important. While maintaining original state of problem after each exploration to make a new exploration with original parameters. And I hope that after solving the 2 questions, this definition makes a lot of sense now. Backtracking uses recursion to explore all the decision spaces and all the possibilities, find solutions using all available options, and exhaust all the possibilities and come back to the stack restoring the original state. All right. And now, after doing both the questions, in both the questions, we have done exactly the same. We have explored solutions while maintaining the original state of the problem, right? And we have discarded the bad solutions, like in the previous question, if left was greater than 0, only then we made the call, right? So for every backtracking question, you can kind of fit it into this template. Find what choices you have at each step, what options are there for the next step. Basically, in the first question we did, there were 2 choices. Either binary number would have a 0 or a 1, right? In the next question, either we would have an opening bracket or a closing bracket. So what are the choices that we have at each step? Recognize that. For each valid choice, I've not written for each choice, I've written for each valid choice. Because in the last question you saw, we made the recursive calls only for valid choices. If we reached an invalid choice, we will not explore that further. Okay, so for each valid choice, make it and explore recursively. Pass the information for a choice to the next recursive call. Okay, so this point was making choices and undo it after exploring. Once you have made that choice, you have to restore everything to the way it was before making that choice. Ultimately, you have to find a base case. What should you do when you are out of decisions? The smallest problem that you know the answer. Okay, that was how would you fit questions into backtracking, any backtracking question. But how would you actually recognize that this particular problem can be solved by backtracking? So if you see a question that mentions something like find all solutions, or you read the question and you feel like there is a possibility, there is a space of possibilities, an array of possibilities, then basically backtracking could be used. Finding all solutions, exploring possibilities, determining whether a solution exists or not. So in some cases, like in the maze question, that question could have been framed in a way that find if this what are the possible paths or not. So if a solution even exists or not, and sometimes even finding the best solution. Also, the constraints of the question. See the constraints. If n is very small, in both the questions that we did, the time complexity was very high. Why is that? Because we were exploring all the choices. For the first question, binary one, the time complexity was 2 to the power n. Exponential. You will mostly have exponential or factorial complexities in questions of backtracking. So n would be given, it's small in the question. So that could also give you a hint that this particular problem can be solved by backtracking. I think we are right on time with that. And that's all that I have today for you people. If you have any doubts, you can ask. I'm here for 2-3 more minutes. You can ask any doubts in either the session or anything related to backtracking or session itself. Okay, Ujjwal, I'm glad that things are clear to you. All right, then, if there are no more questions, we can wrap up. Next session for backtracking is on 2nd of April. I can, Danya, but I will keep it for the next session because we are out of time already. Let me do one thing for you. I'll just explain you what the question is, dice roll, and then you can try it yourself once, right? So in the question, you are given n equal to 2, or n is given some number, and it represents that how many dices you are having in your hand. And for each dice, you will for each dice you have 6 options, right? Because it's a cube and you have 6 faces on it. So each dice will have either a 1 on it or 2, or ultimately basically 1, 2, 3, 4, 5, 6, anything on it. Second dice will also have something like that on it. Third dice will also have something like that on it. So basically what is happening, you are throwing 3 dices simultaneously. Now you have to return what all are the possible combinations that you can get after throwing 3 dices. If you are throwing 3 dices, there are 216 possible combinations, because first choice die have 3 options, 6 options, second also have 6 options, third also have 6 choices. So you see choices word here, you have a large space to explore. The first step is actually very clear. Find what choice we have at each step. At each step, each die, like the die could either have 1, 2, 3, 4, 5, 6, basically 6 choices. For each valid choice, you call recursion and you find the base case. You will reach the base case when n would become 0, basically. If you solve it yourself and try to write a code of it. Okay, but that is basically the question. And yeah, write the code yourself for it, and we can discuss in next session if it's not clear. For next session, I'll either continue from dice roll or I'll start from letter combinations or a bit tougher problems in Pin Sensor roll. All right then, guys, that's all from my side for today. Thank you all for joining after a holy break. And I know this session was scheduled for 18th of April and it was rescheduled to 20th because we did not notice that 18th was holy, which was a festival here. That's why I had to reschedule it for today. Okay, guys, thank you all for joining.
Thank you. Visit verseo.com, subscribe to our channel to know more.